PhD, where I was in serving in US University Science Malaysia between 2014 and 2020. Uh, uh, Going directly into the topic of the session today, it's understanding earthquake seismology. It's a bit introductory with some information not so advanced to fit with the audience. Uh, as I told, this is like uh, beginners or starting career, of course, with many of well experienced colleagues and friends of mine in Malaysia. Uh, and the start is like from the Holy Quran is the Surah Al-Zalzala. بسم الله الرحمن الرحيم إذا زلزلت الأرض زلزالها وأخرجت الأرض أثقالها وقال الإنسان ما لها يومئذ تحدث أخبارها بأن ربك أوحى لها. When the earth is shaken with its final earthquake and the earth discharges its burden and man says what is wrong with it, that day it will report its news everything from the start to end. This means that the last day will be like a big and huge earthquake. I started with this as introduction to our talk today. The overview for this talk will be why study earthquakes, where earthquakes occur, the geographic distribution of earthquakes, sources of earthquakes, why earthquakes occur, seismometry, seismic waves, source parameters, and finally, I hope this will be interesting for us, the earthquake prediction and seismic hazard assessment. This is very important, and many people are asking about this point. Why study earthquakes? Earthquake has a huge impact on human and on the building. Excuse me, the building, the structures, and this is like two examples of what earthquakes can do if strong enough, and how it can disrupt the economy and also can cause casualties. I tried to collect some information about the statistics from World Health Organization about the impact of earthquakes on human. As you can see, earthquakes for the period from 1998 to 2017 is the main, the highest contribution of casualties by 65%, whereas other source of natural disasters are somehow far below. This is the fueling reasons why we need to go for understanding earthquakes and try to avoid. I'm sorry, I guess maybe something went wrong with the presentation. So we go back. Uh, Also from the number of occurrence of this catastrophe, the earthquakes, luckily, alhamdulillah, is the third among other natural hazards following flooding and storms. Uh, and this also one of the points that we need to understand why uh, it occurs, the numbers, the frequency, uh, for many reasons, to avoid their negative impacts on humans. Also, the economic loss.
Hello, doctor. Can you hear me? Because I cannot hear you currently. Hello, Professor Amin. Can you hear me? Um, Audiences, can you guys hear me? Can you guys hear my voice? Because I cannot hear Dr. Amin's voice right now.
We can hear you, but I also cannot hear Dr. Min voice.
Oh, okay, okay. I think he's currently having problem with the connection. Right, thank you for your update. Never mind. I can maybe we give him some times.
Hello.
Yes, Doctor. Hello, can you hear me? Professor Amin, can you hear me? Sorry, everyone. I think Professor Amin is currently having problem with his internet connection. So we'll give him some time to get back into here because currently he is not in this meeting right now. Maybe he's trying to uh, get into the connection back.
Can you WhatsApp him to find out? Hello?
Yes, hello. Yes, I think Professor Amin is in this meeting already.
Maybe there is a network problem occurred.
Oh, okay.
Okay, I will share again this.
Yes, okay, doctor.
Okay.
Okay. We can see your slides now, Professor. Professor, is your connection over there okay? Hello, Professor. Is everything okay? Can you hear my voice? Yeah, so we can see your screen now.
Can you hear me now?
Yes. Can you hear me?
Yeah, I hear you clearly.
Or sorry?
I hear you clearly.
Oh, okay. Because your voice is breaking up.
Sorry for that. Is it okay to continue?
Yes.
Okay. I apologize for all participants because of this technical problem. We were talking about the impacts of earthquakes on human lives and human economy. And plans for mitigation and preparedness for earthquake phenomena. This is extremely important for countries with high seismicity rate, but I believe it's also of utmost importance for countries like Egypt and Malaysia, where we have earthquakes occurring at less frequent rate because uh, the people are not prepared and not aware about the plans the government authorities established for the preparedness of earthquakes because of long time between earthquakes. Another point why we need to study earthquakes is the distribution of earthquakes. As you can see, this is a map for earthquakes between 1977 and 1992. As you can see, earthquakes occur in certain zones, and later on we will understand that these zones are the plate boundaries. So as we are going to discuss briefly later on, earthquakes was one of the important information 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 on which the plate tectonics theory was established. Another important information is the study of the interior structure of the Earth. Many of us understand that the Earth is composed from a crust, mantle, and core, and the core has a certain outer core and the inner core, and so on. But no one asks himself how we obtain this information. This information uh, this information was obtained from the analysis of travel time. Sorry, I feel someone is taking control of the presentation. Is this okay? Hello? My God, Subhanallah. Do you, do you hear me?
Yes, Doctor, we can hear you. But we cannot see your
Okay,
screen right now.
okay. Okay, can you see it now?
Not yet, sir.
Can you see it now? Things look
No, from my screen it only appear
no?
white. How about the other audience? Can you see the Professor Amin's slide?
No, I cannot see. No slide.
With just white screen.
No, okay.
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 Just nothing.
Okay, okay.
You find it empty, but it can be moved forward to the north by during the December to the next.
Can you see now?
No, I still can't see. Maybe you can try to send me your PPT, and maybe I can try to share it from here. I can
Okay.
navigate your slide from here. Yeah. Wait, I give you my email in the chat box.
Okay.
Right. My email is already in the chat box. Professor, have you sent to me your PPT?
Just a moment.
Just now, okay.
I sent to you via email.
Oh, okay. Because I haven't received it in the email box yet.
From my side, it's already sent.
Sorry.
It's already sent from my.
From your side, okay. Because I'm not sure why, but
Have you checked the trash folder?
sorry. You were saying?
Did you,
The trash folder.
the
We
junk,
cannot hear
maybe
you.
it was, no, maybe it went to the junk. It's not received by now.
Mm, I'm not sure if my email is having problem right now. Wait, let me see. Sorry, doctor. I think I'm having problem with my Outlook email. Can you try to send me again to my Google email? Wait, I share with you the email. Right. Can you share again, doctor? Using my Google
Okay.
email that I've shared the email in the chat box.
Okay, I sent your Gmail mailbox just right now.
Okay, that's all right. Thank you.
Welcome.
I'll check my email inbox. Right, I received your email just now. Let me download the PPT. Okay, I'll try to share my screen now. Right, can everyone see my screen right now?
I can
Yeah.
see.
Yes, okay. All right, so I will navigate your slide from here, Doctor. Okay. So,
Okay.
all right. So
So
where was
next one,
next one?
we
This
go
one.
to yeah. So
Okay.
yeah, I was just saying that in addition or besides the economic and the human impacts of earthquakes on us, also earthquakes prove to be very important for obtaining information about the Earth system. For example, for this slide, this is where earthquakes occur, and we can see that earthquakes is not like a cloud, like dispersed in space, but it goes into certain zones, and also these zones helped in the development of the plate tectonic theory that we are currently use for understanding the Earth as a system. Next slide, please. In addition, the information that we obtain about how the interior structure of the Earth looks like and our understanding about the structure classification into crust, mantle, and core, and many other information about the deep structure we obtained from the analysis of the travel time of earthquake signals or phases that being recording worldwide in many places. As you may know that the radius of the Earth is on average 6,370 kilometers, and this radius is huge that we cannot obtain any information about from direct direct probing like well logs, like wells, the deepest wells in Russia or former USSR at like 12 kilometers. So comparing 12 kilometers to 6,000 is very small information we can get from logging. So this also is another important reason why earthquakes need to be, why seismology need to be studied. Next slide, please. Okay. Historically, human wants to know what is the source of earthquakes, why earthquakes, what is the initial point for earthquakes. So at the earlier time, they were like superstitious. Middle East, we have other superstitions about
And can you hear me, Doctor? Hello, Doctor. Can you hear me right now? I think there may be some interruption on Dr. Amin's connection. Doctor, can you hear me? You can hear me, okay.
Can you hear me?
Yes, we can
Hello?
hear you now. Yes, Doctor.
Can you hear me?
Yeah, we can hear you.
Hello?
Right. Hello. Yes, I can hear you. Is it okay? I can hear you now, Doctor.
You hear me?
Yes, I can hear you.
Okay, we continue or?
Oh, yes, we can continue.
Okay. So scientists started to realize that earthquakes occur due to huge faults, and the reason in the next slide, please. Okay. And the reason was discovered maybe by chance, not by study. It was in San Francisco earthquake in 1906. There were geodetic measurements before the earthquake, shortly before the earthquake, and we had earthquake in 1906. Then we this scientific team, went 1910 and make another geodetic observation, and he came out with his elastic rebound theory that we have some weak zone in the Earth's crust where the stresses start to affect and accumulate. This stresses cause strain energy to be stored in. Yes, it's okay.
Yes, Doctor.
Okay. So these stresses start to accumulate until certain point where failure take place. This failure in hard rock is associated with release of energy, and this release of energy about 10% of this energy is like it says earthquake shaking, and other energy like chemical energy, like lighting, like many other energy. And then after the release of certain amount of stresses, the rebound take place to get back to a stable point after relieving stress. So this is a cause of earthquake, and the earthquakes is occurring due to faults within the crust of the Earth or within the lithosphere of the Earth. Next slide, please. Okay. Now we come back to the point where how the plate boundary theory, the plate tectonic theory was developed. This one of the feature is related to the depth of focus of an earthquake, and this is called Benioff-Wadati zone. When we have a subduction zone, so we have near the subduction, we have shallow focus, and then when we go away from this, we have deep focus, and this helped to determine the subducting slab, which is very important in the plate tectonic theory. So next slide, please. Okay. So we have from seismology and from the other studies conducted, we have 3 plate boundaries. The uppermost in the right panel, we have the subduction, where we have epicenters or foci of earthquake is going deeper as we go along the subducting slab. And we have the other 2 types of the plate boundaries. The divergent plate boundaries, this is like Atlantic mid-oceanic ridge. And we have also this transform fault that also represent the earthquake, the plate boundaries where we have like strike slip motion, sense of motion. And the San Andreas fault is one of the very clear situation for this kind. The mid-ocean ridge, like the Atlantic and other divergent plate boundaries, like the Red Sea in close to Egypt. The convergence, the upper one is for Malaysia is occurring in Sumatra in Indonesia, that we have both the subduction zone and also we have the thrusting that take place in Sumatra. Next slide, please. The modern seismology started with the introduction of seismometry, the seismographs that helped in measuring and recording the actual ground motion of the earthquakes, and that gave this wealth information that, as we said previously, that helped in understanding the Earth system. Please go next slide. Okay. This seismometry started very early, maybe 2000 years ago, by the seismoscope. And seismoscope is just a tool that can be used to tell us that an earthquake took place. And also it can, this seismoscope can tell us the direction of this earthquake. And this one is the seismoscope from China. And by the way, China has the longest record of historical earthquake. Or catalog. When I'm talking about this, is not because the Chinese were the first to measure or to discuss the the earthquakes seismicity, but they started maybe like 18th century ago. They started to collect information and archiving this information in very systematic way that we can use for determination of seismic hazards and seismic earthquakes, as we are going to say later on in this discussion. Of course, we have in Egypt, we have earlier observation from earthquakes, but it's not like complete like the catalog, the Chinese catalog. Next slide, please. Then, by the end of the 19th century, the seismograph come to focus. And this seismograph, what we have here is two pictures. The left one represent the concept of seismographs, that we have a mass, and this mass is connected with a pen, and this pen is writing or recording in analog way the motion as the particle just below the seismometer start to move, either horizontally or vertically. The right one was very advanced, but maybe 30 or 40 years ago. This is portable seismograph. It's called, I think this is MEQ 800. And it was useful at that time. Before we go into the digital recording that gave great push to seismological investigations. Next slide, please. This is an example of analog and old recordings that we used to have. And this is one of the big earthquake look like. As you can, if you can see that we have like some notches or small boxes along the horizontal lines. These small boxes represent the timing. The distance between two consecutive points is the 1 minute. Next slide, please. This is a digital seismogram example, and as you can see now, we can do filter, we can extend the timing, we can enlarge the amplitude, so we can obtain good information. We can pick the phases that we have, and these phases are actually what we use for analysis and for getting information about the deep structure of the earth and other maybe also shallow structure. Now we can do many things with this digital data. Next slide, please. So what we have on the seismograms is the recording of seismic waves. So seismic waves has two main classification: the body wave and the surface wave. The body wave is like P wave and S wave, and they usually comes first to the seismogram, to the seismograph. And we have the surface waves that is slower and come late in the seismographs. As you can see, also the surface waves keep its energy and amplitude high at long distance compared to P wave. For damages that take place, it's mainly due to either S wave, that for areas close to the epicenter, or due to surface waves for areas away. So for example, for Malaysia, the main effect comes from the surface waves, not due to body waves. In addition, the surface waves has less small or less frequency or lower frequencies compared to body waves. So this lower frequency usually affect the tall buildings, like high-rise building in like Kuala Lumpur, for example, and also for water tanks and bridges. All these are maybe affected by large earthquakes from Indonesia, from Sumatra. And I believe this must be taken into consideration for the new building to take place. Alhamdulillah, we don't have yet casualties or damage due to these earthquakes from Indonesia, but we have to take care for this. Next slide, please. Okay. Earthquake source parameters are location and origin time, focal mechanism, and size. Where earthquakes occur, that we saw from the global seismicity map. How we obtain this? We use location by using geometry, or by computer software that can analyze the travel time and convert this travel time into the location, lat long, and depths, in addition to origin time. Next slide, please. So here we have like a block diagram show us the when the earthquake occurs deep in the earth. This in the subsurface called the focus, and the point vertically on the surface above the focus we have what's called epicenter. And this circles is the seismic waves propagating in all direction. and the travel time is the time taken for each phase, seismic phase, to reach the station that record this earthquake. Next slide, please. This is the location of earthquake in older time using the geometry. So by obtaining the travel time, or the difference between the S arrival time and P arrival time, we multiply by a factor that is related to the velocity structure. So multiplying the time with multiplying the time and with velocity, we obtain the distance. So for each station, the epicenter may be occurred in any points along the circumference of the circle. We need at least 3 stations, so we plot these 3 circles according to the distance between each station and the epicenter. They usually intersect at a point. This point is the location of the earthquake. Next slide, please. Okay. The second one of the source parameter is the focal mechanism. So the focal mechanism was observed early in 1923 in Japan, when they have recording the for many stations surrounding an epicenter of an earthquake, and figured out that the onset, the motion at the very early phase that arrived to the station, that this onset takes certain geographic distribution, and when they continue with geologic information, they found out that this is related to the type of faults that cause this earthquake. And later on, when the body force equivalence was discovered, that this body force equivalence was used for modeling, how to model the earthquake, representing the faults. And they found out this mostly the earthquakes are double couple. It's like you know, couple forces at certain distance apart, but working in opposite direction. So the best fit is mostly a double couple, and from this we can obtain, as you can see from the left panel, the excuse me, one of the audience is opening his mic. Maybe he close mute his mic, please. So as you can see from the left panel, that we have some feature. This is called the beach ball, representing each kind of faulting. As you can see also, we have dark and white quadrants, and this related to either the onset of earthquakes is compression or compressible up or down. And from this we can obtain whether we have left lateral, right lateral, normal or reverse faulting. And all these are important for modeling the ground motion that is important for seismic hazard, and also for mitigation and preparedness. Next slide, please. One of the important parameter also, the size. The size is related to the energy that is released from an earthquake. At early time, before the seismograph take place, It was intensity was the only way we have, and then the magnitude, and finally the seismic moment. Next slide, please. This is GMA intense scale, the Japanese meteorological agency, and this is the intensity scale. It's a descriptive measure. As you can see from this slide, it tells you that from scale 0 to 7, that how people feel when an earthquake occurs. For example, feeling like dizzy, and also maybe frightened due to the shaking, running outdoor when the shaking is very severe, and then the effect on structures like hair cracks in the building, or at the end the total collapse of the building. So all these and many other scales are descriptive. We describe what we felt, and then we try to categorize this feeling into a certain parameter, and this certain parameter is used to also determine where is the expected focus. But as you can see, that this is all related to human and man-made structure. When an earthquake occurs far away in a desert, for example, or in the sea, maybe our intensity measure will not be correct. Next slide, please. Later on, in 1935, Richter and Gothenburg conducted the huge survey and research. They were working in California, and their place were close to where I served at Berkeley Seismological Lab. And they started many trial to weigh. Size is like to weigh something, is to measure something, not to be descriptive, but to be quantitative. So they found out that the earthquakes in California are attenuating in certain manner, as you can see.
Hello, doctor. Can you hear me? I currently cannot hear your voice. Doctor, if you can hear me, maybe I think there's a connection problem on your side. Maybe you can try to uh leave this meeting and try to join this meeting again. I'm sorry, everyone. I think there's like problems with the connection from Prof. Amin's side. I'm currently
Hello, you hear me?
hello, doctor.
Yeah, I feel something is going wrong with this. Somebody is playing with this. Sometimes I found my mic is closed, playing with the presentation.
Oh, okay.
But if you hear me, we can continue.
All right, sure. I can hear you.
Okay.
Right. So everyone can see my slides, right?
I can see it. Yes. Okay. So they choose an earthquake as the unit. They like the 1 meter scale, like the kilograms. So they choose the magnitude, the earthquake with a maximum trace amplitude of 1 millimeter at 100 kilometer distance from the epicenter. And this was the first trial to study the size of earthquake um, in a quantitative way, and both Richter and Gutenberg worked together for almost more than 20 years. One of the audience said that he cannot see the presentation. Okay, everybody can see the presentation? Hello? Hello, somebody muted me. So many audience can see, but maybe one um, uh, some cannot see. I'm not sure why. So we continue or we wait? Yeah. 1:14. You hear me? So some audience can see the presentation, others cannot. But I feel those who can see is are more. Is it possible to go on? Okay, can we continue? Chief Fatin, can you hear me? Okay, I'm not sure what to do now. What to continue, or I hope the moderator can help. Hello?
Hello, doctor. Can you hear me now?
Yeah, yeah, I
Okay.
can hear you clearly.
Right. I'm so sorry. I think just now I have problem with my mic. Yes, we can continue. I will share again the slides.
Okay, thank you. Okay, so we end quickly this. So they use the amplitude with distance for one earthquake as the measuring unit, and later on they continue to convert this into energy, and also this is for California only. So they did go for other earthquake size measure, like body wave magnitude and surface wave magnitude, and also duration magnitude. Each is related to certain phenomena. But all these earthquakes have certain limitations called saturation. It cannot give information about or the correct size of an earthquake greater than say magnitude 8. So next slide, please. So the scalar seismic moment came into play, and from this scalar seismic moment, we can have direct physical measure about the energy that was related. This is related to three parameters: the modulus of rigidity mu, the dislocation or the slip along the fault plane, and also the area of the fault plane. And from this scalar seismic moment, we obtained the new relation for moment and magnitude scale that suffers no more from the saturation. And that's why for earlier time, we had no earthquakes with magnitude greater than, say, 8.5 or 9. But now some earthquakes are like 10 magnitude, 10, 9.6, and 9.7, like the one that occurred in Sumatra in 2004. Next slide, please. And this shows the how we estimate the moment, the scalar seismic moment from seismograph. We take certain window and we do Fourier transform. The panel to the right represent how the spectrum looks like. For we have the steel, the level, the horizontal level, and the starting point where the spectrum drops. This is called the corner frequency, and this corner frequency is related to the size, the area of earthquake, and from this spectrum we can obtain the scalar seismic moment, and later on we can use this information for the determination of moment magnitude. Next slide, please. So this is the, I believe, the fruitful point of this presentation, which is the earthquake prediction versus seismic hazards. Lately, I received some question like this. Is there any possibility right now for earthquake prediction? The answer for now, we don't have. So earthquake prediction requires acceptable accuracy for the determination of the magnitude, the location, and date and time where the earthquake will occur. For example, if we have an earthquake expected to take place or predicted to take place in certain big city, we need to make sure that the magnitude is that big that we need to take certain measure, and also we need to know exactly where the earthquake will occur and what time. For example, if we are taking action to evacuate the people, then the situation require where to migrate them, where to move them to other places. So the location is important, and the time also, date and time is important, that we need to take certain action before and after the expected time of earthquakes. So they tried many experiments and tests throughout the 20th century. Only one was successful in China in 1974, but all other attempts were not correct, and that's why they moved to the seismic hazard assessment. And the seismic hazard assessment is introduced by Cornell in 1968. So instead of predicting the earthquake for evacuation and so on, we try to understand or to calculate the probability of certain level of ground motion with time, and this measure is used for measuring or for expecting the forces that will take place or affect the buildings and the other man-made structure, and then take the necessary measure to build earthquake resistant structure for like bridges, like water tanks, like buildings, and so on. Next slide, please. We have two options for the seismic hazards. Either we use a deterministic. That deterministic depends on determining the controlling earthquake. The controlling earthquake is the earthquake that, from the history that we obtain, that give us the information that this is a big one, the biggest one. So we use this one for the design of the earthquake resistant structure. And this somehow is good for mitigation, but the problem is that we will sometimes cost much, because maybe in the time life of the building, this earthquake will not take place. And also we have another risk that maybe we have earthquakes not recording in our history. So maybe we come out with some surprise, and we have either we pay a lot of money without need, or we build our buildings with less parameters. So when a big earthquake takes place, it will have a big problem. The other one is a probabilistic, that we studied the different different sources that affect our area, and we build like frequency distribution, and this frequency distribution relation is the base for the probability. So we use this to build the probability model, and this probability model gave us the ground motion levels that will affect our structure or our region, and how this probability take place in time or in time periods. So for example, the probability of a big earthquake in 50 years time is less than the probability in 100, and maybe less than in 2000. For example, we have a study conducted in 1989 in California after the famous Loma Prieta earthquake, and they came out with the statement that California is expecting big earthquake that take place in the next 30 years. And when I was there in California, they were make reinforcement and preparing plans for mitigating the earthquake. So after, say, now it's like 32 years, the earthquake didn't occur yet, but this doesn't mean it will not take place, but it means that the probability that this earthquake will take place is increasing. So maybe in the next 5 years or next 10 years, we have big earthquake affecting California. Next slide, please. I think maybe this is the last one. So I'm sorry for the problems that we saw in this, we witnessed or experienced it in this session. Thank you for your patience and attentions. And maybe we can go for a question and answer session. Thank you very much.
Right. Yes, thank you very much, Doctor, for your very insightful sharing on the understanding of the earthquake seismology. And so, since it's already 4:30, but we can take like about 5 to 10 minutes to have a Q&A session. And so for the audience, if you have any question that you'd like to ask or discuss with Professor Amin, you can do so by turning on your mic or typing your question in the chat box. Yes, please unmute your mic if you have a question to ask to Dr. Amin.
Hello, can I ask a question?
Please.
Yeah, can you hear me? You can hear me?
Yeah, can you? Yes, can.
Yeah. Okay, number one is, so your conclusion is you cannot predict earthquake, right? That's the number one conclusion.
Yes.
Okay, and number two is your geographic distribution of earthquakes, the big map, global map, right?
Yes.
You show the map, geographic distribution of earthquakes. So in the case of Peninsular Malaysia, Peninsular Malaysia, is it in the Ring of Fire? Is Peninsular Malaysia in the, on the left side, Peninsular Malaysia, is it in the Pacific Ring of Fire?
Okay.
Yeah. Okay. Peninsular Malaysia on the left side.
Yeah. I know. But I stayed there for 6 years.
All right. Okay. Peninsular Malaysia, is it located within the Pacific Ring of Fire?
Okay. No, this
No,
Peninsula Malaysia not in the Ring of Fire, but close to Peninsula Malaysia. This Sumatra is also active one. The Ring of Fire is in the Pacific, which maybe starting maybe from Philippines, Japan, West. But we have high seismicity in Indonesia, and from the geography, I can see like Indonesia is surrounding maybe Malaysia, the Peninsula of Malaysia, and this Sabah and Sarawak in Borneo, like taking Malaysia in a hug. It's surrounding from all direction. So if we expect big earthquake, so maybe from the effect come from Sumatra for Peninsula Malaysia. Sabah has also local earthquake activity. I believe in 2016, a big earthquake took place in Kota Kinabalu area that caused also big some damages there. For prediction, our understanding of the phenomena, we have some points still not covered. Now, major faults is monitored with geodetic measurements, geodetic instrument, but still we do not know where exactly the earthquake it would take place, and still we have not correct timing for when the earthquake will occur. As I tried to clarify, we need, in order to take action, we need to take to have good information about this, where, when, and the magnitude. So far, no, we can't.
Okay, thank you.
You're welcome. Okay, maybe I okay, I have a question on the chat box. I would like to ask, it may be silly. Nothing is silly. It's usually the data is collected by governmental organization, private organization, or academies. Are there companies that actively study this actively for reasons other than research and development? What kind of job opportunities are there for graduates who have interested in seismology? How about the Southeast Asia countries? Actually, because earlier this was very expensive to get this instrument, and it was distributed with like grants or like collaboration between big bodies. And also the government, when they experienced a big earthquake, sometimes they started, like in case in Egypt and also in Malaysia, started to deploy seismographs in certain places. So like a Bukit Tinggi earthquake in 2009, there is some stations took place after Kota Kinabalu earthquake. Also, we have more station in Sabah and also in other places. But now there is Rabi Sheikh. This is like free, that you can get your own seismograph. You can get your own seismograph and you can use it for jobs. Mainly, it's related to study of the effects. It's like seismic hazard assessment, like also the determination of the site effect, the amplification of ground motion and certain sites. So these are the available, but also it's limited to some companies that have the resources to do so. After all, seismology is part of geophysics, so it's you can try to do like scientific group, make a company, and try to provide services for those who are interested in building certain places for entertainment, for compounds and so on. All this can, especially if we have like earthquake activity, or if we have landslides, or also earthquake, ground motion can trigger landslides. So, and also you can study this with explosion, blasts due to mining, and so on. So the chances are there, but you need to try and try and try. And I believe maybe you can get what you want.
Prof. Amin, can you hear me?
Yeah, I hear you clearly.
So maybe you remember me, I'm Abdul Ghani.
Of course,
what I want to say actually is more like comment rather than question. It's a very interesting presentation. Unfortunately, it was all broken up by some technical problems. I just want to comment on two things. In Malaysia now, because we are, whether we like it or not, no, we are 400 kilometers and less away from major fault lines in Sumatra for Peninsula. So in the meantime, we also have this latest, I think it's 2017, there's a seismotectonic map which gives the peak ground acceleration PGA values for Peninsular Malaysia, also for Sabah and Sarawak. And then there is also in this document, there is the recommendation for site-specific assessment of earthquake using the VS30 value. So all this actually now has become, for those who are in this involved with construction, for example, it has become very systematic compared to, let's say, maybe before the Aceh tsunami earthquake, where those who were involved in this, they only had bits and pieces of information from which they would try to develop some sort of probabilistic seismic hazard assessment. So it's just to share with also the audience. So in the meantime, there is no more, how do I say, there's no more mystery surrounding this earthquake hazard assessment, whether it's for buildings or whether for geotechnical. Thank you.
Thank you, Professor Ghani. Sorry, let me be on the opposite side, that no, they will still have many things still not resolved. For example, when we compare the studies conducted in Japan, and very detailed study about the seismicity, and the very detailed data about these different effects. We have two clear cases that opposes the idea that it's very totally resolved and no mystery. One is a Kobe earthquake in 1995, where Tokyo experienced damages because the earthquake occurs in Japan Sea, not in the Pacific Ocean, which was not expected for them. The second is the Sendai earthquake in 2011 in March. It was also not expected, despite all the information, all the studies conducted by Japanese and other scientists about the seismicity and seismic hazard in Japan. So no, we still have to do a lot of work. For the first point, for the first comment, yes, the seismicity from Sumatra it's far. It's like 400 and something kilometer. But if we have certain frequency content of surface waves, it can come to some places like, God forbid, like Kuala Lumpur, and maybe the swaying, the short or small distance, lower frequencies of the surface waves can cause a big problem to the tall and certain structure that has natural frequency less lower natural frequency. I believe this is we didn't go to completely resolve all mysteries. We still have mysteries, and so I beg your pardon to have other opinion than what you kindly said. Of course, Prof. Ghani is well known and high reputation professor in geophysics in Malaysia and overseas. Thank you.
All right. Thank you, Dr. Amin, for your explanation, and also all the audience for their questions and recommendations on our webinar's topic today. Right. So I think that would be the end of our 7th Geophysics webinar series. I would like to thank again Professor Dr. Amin for becoming our honorable speaker today. And I believe that all of us have gained so much new and valuable insights and inputs from your sharing just now.
Okay.
And so before we end our session today, just a kind reminder for all, please kindly fill in the attendance Google form link for this webinar, the one that I've shared in the chat box. And so that is all from me. Thank you so much for your participation today, and I hope to see all of you again soon. And thank you again, Professor Dr. Amin.
Thank you very much. Thank you very much. Really appreciate this opportunity. Thank you.
Thank you.